Hey everyone, and welcome back to the channel. Today, we're diving deep into a topic that's been gaining a ton of momentum in the software development world: functional programming. But what exactly is it? And why are so many developers excited about it? Stick around, because by the end of this video, you'll have a solid understanding of what functional programming is, its core principles, and why it might be the key to writing cleaner, more predictable, and more maintainable code. So let's start with the big question: what is functional programming, or FP for short? At its heart, FP is a programming paradigm, which is just a fancy way of saying it as a style of building the structure and elements of computer programs. Unlike object-oriented programming, where you might think about everything as objects with properties and methods, functional programming treats computation as the evaluation of mathematical functions. The key takeaway here is that it avoids changing state and mutable data. To really get a grip on FP, we need to understand its fundamental building blocks. The most important one is the concept of pure functions. A pure function has two simple rules. First, it always produces the same output for the same input. Just like our math function earlier. If I have a function called add that takes two numbers, add 2, 3 must always return 5. It can't return 6 one day because the weather is cloudy. Second, a pure function has no side effects. A side effect is anything a function does other than simply returning a value. This could be modifying a global variable, writing to a file, logging to the console, or changing the data that was passed into it. Pure functions are completely self-contained. They take some data, work their magic, and hand back a result without affecting anything else in the outside world. This makes them incredibly easy to reason about, test, and debug. You don't have to worry about hidden dependencies or unexpected changes in your program's state. Let's look at a quick example. Imagine you have a list of numbers and you want to double each one. In a more traditional imperative style, you might create a loop, iterate through the list, and modify each element in place. That modification is a side effect. In a functional approach, you wouldn't change the original list. Instead, you'd create a new list where each element is the doubled value of the original. Immutability is the second core concept of functional programming. It means that once data is created, it can never be changed. If you want to change something, you actually create a new piece of data with the updated value. This might sound inefficient at first. Aren't we creating a lot of extra objects and using more memory? Modern functional languages and libraries are very clever about this. They use techniques like structural sharing to reuse parts of the old data structure in the new one, making it surprisingly efficient. The benefit is enormous. When data can't change, a whole class of bugs related to unexpected state modifications simply disappears. Have you ever chased a bug for hours only to find that some random part of your code was changing a variable when you didn't expect it to? Immutability makes that impossible. This also has huge implications for concurrent and parallel programming. When multiple threads are trying to read and write to the same shared data, you run into race conditions and deadlocks. You have to use complex mechanisms like locks to manage access, which can be difficult to get right. But if your data is immutable, there's no problem. Any number of threads can read the data at the same time without any risk because they know it will never change. This makes writing safe, multi-threaded applications much, much simpler. Another pillar of functional programming is treating functions as first-class citizens. This just means you can do anything with a function that you can do with any other data type, like a number or a string. You can store functions in variables. You can pass functions as arguments to other functions. And you can even have functions that return other functions as their result. This is incredibly powerful. Functions that take other functions as arguments are called higher-order functions. If you've ever used map, filter, or reduce in JavaScript or Python, congratulations, you've used higher-order functions. For example, the map function takes a list and a function as its arguments. It applies that function to every item in the list and returns a new list with the results. You don't have to write the loop yourself. You just declare what you want to do. This leads to code that is more declarative and expressive. Instead of telling the computer asterisk to do something step by step, you tell it asterisk what asterisk you want to achieve. Let's quickly touch on filter and reduce as well. The filter function, as you might guess, takes a list and a predicate function that returns true or false. It returns a new list containing only the elements for which the predicate returned true. Now, you might be thinking, this all sounds great in theory, but where can I actually use it? The answer is pretty much everywhere. While there are purely functional languages like Haskell and Elm, the principles of functional programming have been adopted by many mainstream languages. JavaScript is a fantastic example. With the introduction of arrow functions and array methods like map and filter, modern JavaScript has become very friendly to a functional style. Libraries like React heavily encourage functional concepts, especially with the introduction of hooks and functional components. Instead of stateful class components, you now write simple functions that receive props and return UI. Python, C#, Java, and many others also have robust support for functional features. You don't have to go all in and switch to a pure functional language overnight. You can start by incorporating these principles into the code you write every day. Try to write more pure functions. Try to avoid mutating data. Reach for map and filter instead of writing a manual loop. So, to recap, functional programming is a paradigm that treats computation as the evaluation of mathematical functions. It's built on a few core principles: pure functions, which have no side effects and always return the same output for the same input; immutability, where data cannot be changed after it's created; and treating functions as first-class citizens, which allows for powerful patterns like higher-order functions and composition. The benefits are significant. Your code becomes more predictable because there are no hidden state changes to worry about. It's easier to test because a pure function can be tested in complete isolation. It's better suited for concurrency because immutable data eliminates race conditions. And it's more declarative and readable because you focus on what asterisk you want to accomplish, not the step-by-step instructions of asterisk how asterisk to do it. Is it a silver bullet that will solve all your programming problems? Of course not. There are situations where an object-oriented or imperative approach might make more sense. But having functional programming in your toolkit makes you a more versatile and effective developer. It gives you a new way to think about problems and a powerful set of tools for writing clean, reliable, and maintainable software. If you're looking to level up your coding skills, I highly recommend giving it a try. Start small and see how it can improve your daily work. Thanks so much for watching. I hope this gave you a clear introduction to the world of functional programming. If you found this video helpful, please give it a thumbs up and consider subscribing for more content on software development and programming concepts. If you have any questions or want to share your own experiences with FP, drop a comment down below. I'd love to hear from you. See you in the next one.